All right. Okay, so let's get started. What is it? I don't have any announcements. So this week, I think the TA, one of the TA said that he's going to talk about decision trees in the recitation. So if any of you are interested in knowing more about decision trees, we are not going to cover it, uh, but he's going to talk about it a little bit, but more about how to use it rather than what it is. Well, if you look at it, decision trees don't have too much of theory inside. It's a fairly sort of a heuristic-driven learning algorithm, and that is why I don't uh, talk about it in the class, but it certainly is a very useful machine learning tool. So if you want to use something in practice, what I always tell the students is that if they want to compare their algorithm with like a baseline, always try to go for decision trees or random forests, which are like collection of trees. All right. But today we are not going to talk about decision trees. We are going to talk about more about regression. All right. Any questions before we start about regression? All right. So these are the things. Well, not so over here. Things in sort of very faded are the things that we have talked about so far. Right. In fact, we covered all of this last week. So we talked about linear regression. We formulated the problem. We said, okay, we can look at it in two ways. One is more probabilistic, and the other was we can look at it in a geometric way, right? Then we saw a few ways to learn the parameters. So we saw one standard least squares approach. We saw one more maximizing the likelihood approach. Then we looked at some of the issues with linear regression. One of them was, of course, that it is too simplistic in many cases. We looked at how to deal with that by introducing nonlinear basis functions. Then we saw another issue with linear regression, which was the issue of correlated inputs. And then we saw an issue that arises from nonlinear regression, which is it tends to learn too complicated surfaces or too complicated lines or planes. And then we saw a standard approach to address all of these issues, which is regularization. And we saw two different ways of doing regularization. So one was ridge regression, and another was lasso, right? For ridge regression, I guess you will see more of ridge regression in your assignment because you are supposed to implement the learning part of ridge regression. The testing part, the prediction part of ridge regression is exactly the same as linear regression, right? Again, it still has the W, right? Even lasso has the same regression equation, which is y is equal to W transpose X. It's just how you learn the parameters, right? So we saw different ways of doing that. So today we are going to look at another way of doing regression, which is Bayesian regression. All right. So Bayesian, as we had talked about a long time back, right? So in probabilistic learning, whenever we talk about Bayesian learning, it means that your parameters also become random variables, right? So in frequentist statistics, your parameters are set, right? And then you estimate your parameters by maximizing your likelihood. But in the case of Bayesian regression or Bayesian statistics, we assume that our model parameters themselves are also random variables. And then we sort of, when we model them as random variables, that allows us to set priors on the weights or on the parameters, and then we can compute the posterior of the weights by doing posterior times likelihood, or prior times likelihood. So in fact, for your gradients last week's quiz, you might have already done that a little bit, right? So I guess you have already seen all this prior posterior business before. So I didn't want to wait for another week for you to take that, do that question. All right. So what is Bayesian regression, right? So in Bayesian regression, so first thing is Bayesian regression is pretty much like regression. There's no difference except that your W, right, also becomes a random variable, right? Which means that now you can put a prior on W, okay? So this is the prior distribution of W. We say that P of W is a random variable, which is a multivariate Gaussian with no, all the components are independent. So let me write it more here. So we are trying to put a prior on W, right? So what is W? W is your weight vector. And W is in RD, which means that's a d-dimensional vector of weights, right? So you can set a prior on W, an appropriate prior. So one of the priors that we have seen in our class is for a vector is a multivariate Gaussian, right? So one of the priors that you can set on W is a multivariate Gaussian. So a multivariate Gaussian has two parameters, right? It has a mean vector. Let's call it all right, for now, let's call it some mu 0, right? So mu 0 is also going to be in RD, right? That tells you that this distribution, where is it centered, right? And then you will also have a covariance matrix, which is a D cross D. Typically, we write it like this, right? So it's a D cross D matrix. So, or you can say that it is a D cross D matrix. This is the covariance matrix. However, since we are going to set this prior, right? So it's usually very hard to set a prior with so many entries. So this one has D square entries. Of course, this is symmetric. It's a covariance matrix. That means it has, D times D minus 1 by 2 entries, right? But there are still too many, right? So to simplify that, what we assume is, that this matrix is diagonal, which means it only has non-zero entries along the diagonal. Everything else is zero. So only this part is non-zero. The reason we do that is because then it helps us reduce the number of parameters that we have to set. Because remember, prior is something that you specify, right? So if you are saying I'm going to specify a covariance matrix, then if you don't put any simplification constraints on this, then you have to specify too many numbers, right? And that typically becomes hard, right? In general, in machine learning or any data mining activity, you want to reduce the number of things that you specify, because remember, these are the things that you have to almost come up, pull them out of your hat. So if you have so many of them, there's a chance that you can get wrong, right? So what we say is that we assume this is diagonal to keep it simple. In fact, we make another constraint which says that every diagonal entry is same. Okay, so we just say that every diagonal entry is equal to some tau square. So tau is some number that you specify. But you essentially say that every diagonal entry in this is diagonals is tau square. So you have simplified your sigma naught to pretty much one number now, right? Just to make it simple for ourselves. But in reality, if there is a reason for you to believe that you should specify a different prior, you can set it, right? It's not, nothing is going to go wrong. It will still be correct. But in practice, we typically assume that our entire this is just, so mathematically you can write it like this. This is equal to tau square I, where I is an identity matrix. Right, so this is the prior that we typically set on the on your Gaussian, on your weights, right? So you can also think of, so because we have no non-zero off diagonal entries, that means essentially what we are assuming is that this multivariate Gaussian is just a collection of independent Gaussians, right? So we can also say that W is a set of D independent univariate, right, Gaussians, because there's no non-zero off diagonal entries, right? So that is that. So that gives you a prior on W. And now what we need to do in Bayesian regression is, given some data, we need to compute the posterior of W. So we have P of W, right? before knowing any training data, we know what P of W is. We want P of W given D. This is a posterior, right? Once we have seen this, so it's kind of like machine learning, right? So training. So we start with this and we correct it so that it also fits the data as well. So now we will see how to do that. I mean, we won't see it that much because we already know how to do that, right? So remember, this is posterior, this is prior. So posterior in general is written as, or is proportional to, prior times likelihood, right? And then typically we also have a normalization factor in the bottom, but that will be same for everything. So we can write it like this, right? Which means we already have prior, we can bring in the likelihood, right? So the likelihood is of the data set, right? Always. Likelihood is what is the probability of your data set given your model parameter, right? And we know how to compute that because this is essentially, you have the training data, so you have y's, and each y is a random variable, so you can compute that, and I'll show you how to do that. All right? Any questions so far? All right. Right. Yeah, so it's fairly standard, right? So what you do is, now you know what is your P of y given D. So let me switch here. I don't want to write so much of math here. Right. So on the screen, what you see is this equation, right? So this equation is nothing but the total posterior, okay? So now you want to find the W, right? So posterior of W will just be this, right? It's going to be the prior times the likelihood. So this part is likelihood. Remember, the likelihood is nothing but the probability of each training data point, and you multiply it all together, right? So the probability of each data point is, according to the linear regression equation, this. I don't know why I have W0 here. Typically, we just write W transpose Xi, assuming that your bias is already in here. But here I'll fix it. But essentially, this is, you're taking the probability of each training data point, yi, right? And remember, in linear regression, we assume that yi is distributed as a normal distribution with mean of W transpose Xi, and the variance is this, right? So when you multiply all of them together, that becomes the likelihood of your data set times the prior, right? So prior times likelihood, that gives you your posterior, right? It turns out, and that is what we saw on Monday, right? Last Monday, is that when you multiply a lot of Gaussians together, the resulting distribution is also Gaussian, because because Gaussian's conjugate is Gaussian, right? So which means that if you started with a Gaussian distribution, the posterior is also going to be a Gaussian, and that is not some magic, right? If you really work this out, because you know all of these equations, you know what P of W is. This is going to be 1 over under root 2 pi sigma naught determinant of that times everything, right? And each one of them is also a Gaussian. So when you take all of these mathematical expressions, multiply them together, what you will see is that the resulting posterior will also look like a Gaussian. All right. So the posterior is also a Gaussian. Now somebody could say, I don't want a distribution over my W. I want one W, right? Because remember, when you are going to use it for your prediction, you're going to do W transpose X, right? Which means that you need one W, one best W. In the case of general linear regression, right, we always got one W. Where is that? Like here, right? For ridge regression, we got one W, right? Which is this. Now we can use it for prediction. But for Bayesian regression, so far, what we have is a distribution over all W's, right? Now, how do we get one W? We can maximize this, right? So we can maximize this, and that is called the MAP, right? The maximum posteriori estimate. by maximizing this equation over here. And if you maximize, in fact, we typically maximize the log of the posterior just to keep the, instead of summation, these products, we converted it to a summation, and it looks like this. So this part is coming from the likelihood, right? And this part is coming from the prior. So you are saying the best estimate of W is this plus this. Yeah. Right. Right. So is the mode of this resulting Gaussian. Exactly. Right. So the question is that since we are, so what will happen now, and I'm avoiding that math just because it's, it's kind of like a too detailed, right? So what I said so far was that this PW given D, which is the posterior, is also Gaussian, okay? Which means that it will have some mean and it will have some covariance, right? Which you can actually compute because PW given D is nothing but pi I equal to 1 through n P of each data point x yi given W transpose xi comma sigma square. So this is the whole likelihood times P of W, right? Divided by a quantity which is a normalization quantity. Let's call it Z. But Z essentially, if you remember your Bayes rule, this for all possibilities. So it will actually be like an integral, right? Integral over all W's, this whole thing times dW, right? So this will integrate all W. So it's, I mean, it won't have W inside it, right? Once you integrate it out. But and typically in reality, this is very hard to compute, right? Because you have to take an integration over all W's, right? So mathematically, it becomes a nightmare. But because this is a conjugate prior, because W, we are using the prior also as a conjugate of the likelihood, then this computation becomes easier, right? That is the benefit of having a conjugate prior, is that you don't have to do this math, but we will avoid it altogether. Essentially what happens is that this PW given D, you will have some posterior mean, some mean, and some covariance, right? And we can actually get the actual values of this mean and covariance, all right? Now the next question is, how do I get one value of W to use, right? How to get, so question number 1, how to get a single value of W, right? So that I can do W transpose X, some new X comes, I can do this Y star is equal to W transpose X square, right? X star. So I need a single value of W. So to do that, what we can do is we can say, let's get the W that maximizes this posterior, okay? So get map of PW given D. Now since W is a Gaussian, which means that this map will be nothing but the mode of this distribution. But that is just the property of a Gaussian distribution. For other distributions, it could be something else. So in general, what you need to do is you need to maximize the posterior and get the value. For a Gaussian distribution, it turns out that if you maximize it, it will be same as the mean, right? Because in Gaussian, the mean, the mode, the expected value, and the map, they're all the same, right? If you remember the Gaussian distribution for a univariate case looks like this, right? So this is actually the mean. This is also the mode, which is the value at which the probability is highest. And this is also the expected value, which is essentially expectations of E of X, right? That's just a property of Gaussian. All right. So now we can compute the map by maximizing this probability, right? What it turns out is that if you are doing map, this quantity will not have any effect because this one, the denominator will not have W at all, right? Because we are integrating the W out, right? Which means that all you can do is you can maximize this quantity, okay? So to get to get W map, right? We maximize PW given D, or just the numerator of PW given D, because we don't even have to compute this Z at all, right? So if you want to do this, right, since there's a product here, that becomes a little tricky. So you can take a log of this. So you can take or log of P of W given D, log of the posterior. Why? To keep it simple. Right? To keep it simple, we are going to take just the log of this. Now the log of this is easier, right? This becomes a summation, right? And this becomes a log of P of W, okay? And then you can maximize it. Now if you go back to, okay, let's write a little more. So log of this becomes log of, so summation I equal to 1 through n. I'm taking a log of this quantity, right? Log of Pyi given W transpose Xi comma sigma square, right? Plus log of P of W, right? This is the prior, right? Now, if you remember earlier, what I said was we are assuming that this prior is a multivariate Gaussian, but with tau square in the covariance matrix, like this, right? So, which essentially means that it is essentially a collection of D independent univariate Gaussian. So you can then write it as, this part still stays the same, and you can write this as 1 over D, 1 through D, right? A normal distribution centered at some W0 and mean at tau square. Variance of tau square, right? Because each one of these D variables is exactly the same. That's the assumption that we are making, right? In fact, sometimes we make it even more simple by saying W0 is nothing but equal to 0. So we say that it is centered at 0 and with tau square is the variance. So this is what happens, right? And then, of course, this part is also a normal distribution. So you can write that as well. And then this is a normal distribution. Any question? Yeah. Right. That's just the effect of log, right? So log of AB is log A plus log B. That's a standard trick that we use to simplify our mathematics, nothing else. Because maximizing log of posterior and maximizing the actual posterior will have the same effect. It's a continuous monotonic function. All right? Does that make clear? Okay. All right. So what happens now is that if you expand it, right? Well, we have kind of expanded it. So this would start looking like this. Right? So essentially what you want to find is a W which maximizes this quantity. So this part is the likelihood, log likelihood, right? So each quantity inside is a normal distribution, right? And each quantity here is coming from the prior, right? So now what happens is this kind of starts to look like ridge regression. So if you remember in ridge regression, right, we were trying to minimize the error, the squared error, right? And here we were adding some regularization, right? So in the case of Bayesian regression, this prior has the same effect as a regularizer, okay? Because if you look at this, what this prior is saying is that each W, right, needs to be centered at weight 0, right, at mean 0 with some variance. So it is trying to, the solution that will come out of this part is trying to bias it towards 0, right? While this part is trying to bias it towards whatever maximizes the likelihood, right? So it is having this, it has the same effect as doing ridge regression, except that it's doing it in a probabilistic fashion, right? So this tau, right? This tau actually has the kind of same effect as what your lambda has, right? In ridge regression, if we go back a little bit, here. So in ridge regression, this is our equation, right? So here we are trying to minimize our error and put a penalty on your W, right? In the case of Bayesian regression, it has a very similar form, because eventually, even in Bayesian regression, you have forms like this in the Gaussian equation, right? In the Gaussian, you also have the same thing. And then this comes here. So it has very similar form. So in fact, if you work it out, right? If you work it out, what it will give you is that the posterior of W is a Gaussian distribution with mean as this. This is the mean, okay? And this is the variance of the posterior. So if you compare this, right? In fact, I'm going to write it in one place. So I'm skipping a couple of steps of the math, but I think in the handouts it's there. So for Bayesian regression, what it comes, the posterior of W, given your training data, right, D or Y comma X, which is your training data, is a normal or a Gaussian distribution, multivariate Gaussian, with mean, the mean of that distribution is X transpose X plus sigma square over tau square I inverse X, Y. X transpose Y. X transpose Y, right? And the covariance of this new matrix, this sigma hat, is going to be sigma square times X transpose X plus sigma square over tau square I inverse. Okay? So let us focus on the mean quantity. All right? So the mean is X transpose X plus sigma square tau square I inverse X transpose Y. Right? Now, if you remember the ridge regression, right? In so this is the map, so W map. And if you remember W ridge, it looks like this: X transpose X plus lambda I inverse X transpose Y. Right? So it's very similar. The only thing is that instead of this quantity, we have this quantity. All right? So the point here is that ridge regression and Bayesian regression with a Gaussian prior have the same effect. Okay? So if you think about it, the reason that is happening is because when we are making this assumption, right? When we add a Gaussian prior to W, right? What happens, right? So let's assume D is 2. So let's say you only have 2 variables, right? So what we do is we are trying to find the W. So this is W1, W2, or W0, W1. Right? We are trying to find the W which maximizes the likelihood, but you're putting a prior, which means that you want W, let's say this is 0. So you want W from the prior information to be here with some covariance, which means that you are saying that your W should be here and it could be around here, and the length of this or the radius of this circle is basically tau square, right? So you're imposing this prior, right? And then let's say the likelihood tells you that W is going to be here. So then what happens is it's kind of like averaging. So you're biasing your estimate by adding this prior, right? So essentially what you're saying is that you want all of your W's to be closer to 0 by the prior. And of course the likelihood would say something else, right? So that has the same effect as doing ridge regression, because in ridge regression what you want to do is you want to make all of your W's small, right? If you remember the ridge regression discussion from Friday, the effect of that regularizer is that it prefers solutions in which the sum of W square is small. It's closer to 0. So that has the same effect here by putting a Gaussian prior. All right? And this becomes even more interesting is because if you remember that we could have used a different prior here. Instead of using a Gaussian prior, we could have done a Laplace prior, right? So a Laplace prior, in that there is a mode of W effect, right? So that becomes equivalent to doing lasso, right? So there's I won't talk about it much, but lasso has the equivalence of using a Laplace prior with with Bayesian regression. So like Ridge has a equivalence of Gaussian prior with Bayesian regression. Lasso has equivalence for a Laplace prior with Bayesian regression, which means that, remember, the reason we were talking about Laplacian prior is that this is how we do robust regression, right? We try to eliminate the effect of outliers in your training data, which means that lasso will have the same effect. So if you have outliers in your training data, and if you do lasso, that will also eliminate the impact of outliers. Any questions so far? Fantastic. So that's sort of the whole overview of regression. So now you know everything about regression. And then the next question comes, okay, how do you do the prediction, right? So one of the ways to do prediction is just to use the map, right? You compute this map, this value, and use it. But in Bayesian regression, if you remember, you can also do Bayesian averaging, right? So, so these are the two different ways. But then you can use the MLE estimate, which we have done in the past. You can do map, which we saw today, or you can do Bayesian regression, which is you can integrate over all possibilities of W, right? Not yes. Go ahead.
I feel a little lost right now. So is the whole point that you're going to compute the weight and then apply that weight to predict?
Right. Yeah. So our basic machine learning task is prediction, right? We want to predict y given some x. But in linear regression, we assume that y and x's are connected through a w, which means that what you do is y is equal to w transpose x, right? So then the question arrives that how do we get that w, right? What w should we use? So we learned that w from some training data. So today we have, till today we have seen many ways of getting to that W. So that's a learning phase, right? But what happens with Bayesian regression is that since our W itself is a random variable, right? So now what we can either do, so if you think about it, so think of this huge box, okay? This box has all the W's that you want, right? Or your optimal W is hidden in this box, right? So one thing you can do is you can pick the optimal W using your regression, using a learning, and then use that, right? But with Bayesian regression, what it gives you is that with every W, it gives some probability because it's giving a probability distribution. So instead of picking only one W, we say, let's pick every W, but weight it by its probability, which means that if some W is highly probable, then I trust it more. And if something is less probable, I trust it less. So that's just the general notion of this Bayesian averaging, right? We've seen that before as well. So that is essentially what's happening here. What I'm saying is, let's try to predict this new Y star given X star by picking every W, but multiplying it with the probability of that W itself, right? So that W is coming from the posterior. So this X and Y is your training data, right? So we have computed this distribution. Remember here, we said that our W is this. This D is basically your X and Y's, which means that now instead of just taking one W, we take every W and multiply them. All right? Any questions? Yes. How easy is that? So this integral is in reality it becomes a nightmare, right? But in this case, because all of these are Gaussians, and Gaussian is one of the most well-behaved distribution, and that Gaussian equation, that EXP thing, is one of the most well-behaved equations in mathematics, which means that this one becomes fairly easy to do. But in reality, these things become very hard, right? So then you do, in fact, we'll look at it when we do logistic regression, is that we need to we cannot compute this exactly. So then we apply some approximate methods. Right. Right. Yeah. Yeah. Yeah, exactly. So that's a good point. So eventually, what we are predicting is not that y star is 5 or 6. Right? We are saying that our y star is also a Gaussian. Okay? So that means that our predictions are also distributions, which actually works better because now you are kind of giving like a confidence interval. You're saying that the prediction is 5, but with some plus minus variance. You cannot, well, you can use the means of this to draw the lines, and then you can draw error bars on them. So that is actually, in practice, that is more useful than having an exact estimate. Any other questions? Great. So now what we will do is we'll switch to another topic of classification. So what we have seen today, so remember this whole, the last week we started this new topic of linear models, okay? So we have looked at one linear model, that's linear regression for regression or prediction. But now we are going to look at another model which is for classification, okay? And that is called logistic regression. That's part C2. All right. March 27, right. So, so logistic regression is a probabilistic classifier. It's also a linear model, right? Which means that it has this notion of W transpose X. So but before that, I want to talk about something else. So remember that in the case of naive Bayes, right? These were the kind of things that we wanted to compute, right? If I give you a new data point X, I wanted to find what is the probability of Y to be benign versus what is the probability of Y to be malicious, right? And we have done that in fair detail, right? Now, in the case of Bayesian classification, one way to do it is to compute P of Y given X as joint probability divided by the marginal, right? And which can be written as this. So this is the Bayes rule that we have known to love and admire, right? Okay. So essentially what we do here, if you remember in naive Bayes, is that we compute this, right? This is the class conditional probability, and then we multiply it with our priors and the sort of the marginalized value here. So it's kind of it's a two-step process. We estimate the generative model, and then we compute the posterior for Y, right? So what is a generative model? So remember, in distributions, right, in mathematical probabilistic distributions, we also think of them as generative models. The model that generates your data, right? I always want students to imagine distributions as these boxes, right? So every time you turn a crank, a new value comes out. So that is a sample, right? So what we do in naive Bayes or many of these other classifiers is that we first estimate the parameters of our generative model, which is Px given Y, and then we compute the posterior for Y using the Bayes rule, right? But it has been argued that this oftentimes is doing more than what is required. See, what is required is to compute Y given X, right? But what we do is we first compute X given Y, and then compute Y given X using Bayes rule. So we are doing too much to do something that we could do directly. So the question becomes, why not come up with a model which can directly compute this? Okay? So this whole thing is what we call a generative classifier. The reason we call it a generative classifier is because we are computing the generative distribution, or we are estimating the parameters of a generative distribution, and then we are using it to compute the posterior, right? On the other hand is something what we call a discriminative classifier, which we will look at, so logistic regression is one type of discriminative classifier. Now, don't confuse this with the discriminative analysis or discriminant analysis that you are doing for your programming assignment 2. So that is not a discriminative classifier. It just has the word discriminant in it, right? But we are going to talk about discriminative classifiers, which directly compute Y given X, right? So to give an example, right, let's say So the difference between discriminative and generative classifiers. This is a very contrived example, but let's say I want two students to be able to differentiate. So the task here is that I play them some audio, okay, and they have to identify what language it is. In fact, they just have to identify, is it one language or another language. Okay, so let's say there are two languages. So let's say Vietnamese and Portuguese, right? So the task is the student will be played an audio and the student needs to say, is it Portuguese or is it Vietnamese, right? So how do I train a student to do that? So let's say I have two students. So I can take two approaches. Approach number one is that I send the student first to Vietnam, where the student learns Vietnamese, right, from the first principles. Then I send the student to Portugal or somewhere else, Brazil, and there the student learns Portuguese, right? And then the student comes back. So now the student knows both languages. And now I play the audio. The student internally, works out, is it Portuguese or is it Vietnamese, and then tells me which one it is, right? So that is one approach. The second approach is that this student, I just play the student many audios which are Vietnamese audios, right? And I tell the student that this is Vietnamese, Vietnamese, Vietnamese. So play like 100 audio samples of Vietnamese, and then play 100 audio samples of Portuguese, right? So at the end of it, the student might not know the language, but he would know how to differentiate between the two types of sounds, right? So the first case where we send the student to these countries, of course, it's more expensive, and that is called it's kind of like an example of a generative classifier. So you made the student learn the generative process, and then the student did the discrimination or the classification. The other example is discriminative classifier, because there the student didn't really learn the model, right? The student cannot speak Vietnamese or Portuguese at all. But the student can do what it is supposed to do, which is differentiate between the two things, right? So like two different philosophies, generative versus discriminative, all right? And it turns out that for classification, it has been shown, now that is theoretical, that discriminative classifiers tend to do better, all right? And that comes from a topic that I wanted to discuss earlier, but I never got a chance. So this slide might be kind of, something that we have not talked about at all, which is, but I'll still mention it just so that you have some idea of this. So in classifiers, right, what we have is this notion of complexity. Okay, so so there is some measure called VC dimension, which is Vapnik-Chernaskis dimension, VC dimension, right? So that measures the complexity of a classifier. So it has been shown that discriminative classifiers have a smaller complexity than a generative classifier. And it has also been shown that if something has smaller complexity, it would have better generalizability. That we have seen before too, right? So more complex classifiers or more complex models tend to make more mistake in future. So they are poor in generalizability, right? So that is the idea behind generative and discriminative. So it's not part of this course, but it certainly is a very interesting, fascinating line of research. All right? So that is, just a general discussion of generative and discriminative. So now we will see one example of a generative or discriminative classifier. We have already seen an example of a generative classifier, which was naive Bayes. So today we are going to start looking at logistic regression. All right? So logistic regression, what that assumes is that Y, right? So okay, the problem here, let me set up the problem. So you have some input X, which could be a vector, right? So vector of attributes. It could be any, so each element of that vector is a feature, right? It could be real, it could be discrete, anything. And what we assume is that Y given X is a random distribution, okay, is a random variable. So Y is the label that you want to predict. So typically we assume that y is either +1 or -1, 0 or 1, red or blue. Later we will see that y can also take more than 2 values, but finite number of values. So it could be 6 values, 10 values, right? So we say that y given x is a Bernoulli distribution. So y given x is a conditional random variable. Remember, x is not a random variable in this case. Y given x is a random variable, and we assume that it is a Bernoulli distribution, which means that it has only one parameter, which is theta, right? Remember, the Bernoulli distribution is like tossing a coin. So it has one parameter, which is the probability of heads, and that is given by sigmoid of W transpose x. Okay, so remember, sigmoid is 1 over 1 plus e power minus W transpose x. So we assume that y given x is a Bernoulli distribution. So now what we are essentially saying is we are directly modeling y given x, right? So remember here, we are directly modeling y given x. We are not computing it like this. We are not computing x given y. In fact, for logistic regression, we don't model x, which is your inputs, as a random variable at all. All we say is y given x is a Bernoulli distribution with theta equal to W transpose x, right? So it's a classic discriminative classifier. So what happens when a new input comes? So let's say we already know W. So W are the parameters for this logistic regression. So when a new model comes, we toss a coin, right, with this as the heads probability. And if the outcome is heads, we say it is a 1, otherwise it is a 0. Okay? Because it has a W transpose x here, which means it's kind of doing a linear combination of your x's, it means that logistic regression is a linear classifier. So, and I'll show that to you in next class, is that if you look at the boundary that logistic regression learns, it is a line. So it's always a linear classifier. But now comes the learning task. The more exciting part is how do we learn this W? Given some training data, right? Given some training examples, how do we learn the appropriate W? And that we will do from Wednesday onwards. All right. So again, logistic regression is trying to directly model y given x. So it's a classic discriminative classifier, and it does its prediction like this, but now we are trying to compute the W that gives you the best answer, right? So this is just a general sort of geometric interpretation for logistic regression. So it looks a lot like regression, right? In regression, we do W transpose x, right? But the place that it changes then is that in regression, we assume that y is a normally distributed quantity, right? Because y in regression can take any value. But in logistic regression, because we are doing classification, which means that y can only take a few values, right? Here we are assuming y takes 2 values for now, which means we can model it as a Bernoulli distribution with this as the parameter. But in Bernoulli distribution, remember the parameter can only range between 0 and 1, right? Because it's the probability of heads, which means that you cannot just do W transpose x, because W transpose x can take any value. So we apply the sigmoid on it, because the effect of sigmoid is it squashes your inputs, right? So whatever you give sigmoid, it will only range between 0 and 1, right? So that's sort of the effect of sigmoid. And then what we do is we say if the output is 0.5 or more, then it is one class. If it's less, then it's another class. So that is sort of the whole setup for logistic regression. And then from Wednesday onwards, we will look at how do we train, how do we learn the weights given some training data. Any questions so far?